Okay, good. So thanks for the introduction and welcome everyone. So I want to talk today about some work we've been doing in the team about light in complex media. And this is illustrated by the picture you see behind of this Eiffel Tower. And if you wait a little bit and you look up, and on a normal day in Paris, you will see a lot of clouds. And then the Eiffel Tower disappear in the cloud. I don't know how it goes with with a zoom compression, but this is just to illustrate the phenomenon that I want to discuss. So first, let me introduce the team. So we are a team of about 20 people in the heart of Paris, with two PI, myself and Hilton Barbosa de Aguiar. And really, our goal is to understand and exploit the complexity of light propagation in complex media. And let me just explain what I mean by that. First, I want to speak about turbulence, which is really when you have just a small perturbation of the wavefront because of, for instance, perturbation in the propagation medium, in which case you have basically an aberrated imaging system, which basically blur the image, okay? And we know a conventional solution for that is adaptive optics, where you basically take this aberrated wavefront, and in real time, you want to basically measure and compensate for that in order to flatten them with an active element, like a deformable mirror. And this is the way you can basically get very high resolution image in astronomy, for instance. So the phenomenon that I want to discuss today is much more stringent than this. It's basically scattering. And this is illustrated in this picture where you have really ballistic light coming from the sun. And the blue color of the sky is really single scattering of the light by the air molecules. And the phenomenon of multiple scattering is really the clouds, where the light has been scattered many, many times. And it's really this whitish opaque medium that light has a hard time to penetrate. And if you want to show what happens, I think it's well illustrated on this simulation where you see a laser coming from the left that will enter the scattering medium, where each point here is a scattering element, and the pulse will basically enter. The ballistic light will disappear very, very quickly, and you will see a very complicated interference pattern that is basically called a speckle pattern. So it's really this deep multiple scattering regime that we are interested in, where there is no more ballistic light and extremely strong spatial and temporal perturbation. Still, the coherence is really this interference phenomenon that you can see that is maintained, and this is the hope, the tool that we can use to exploit this scattering process. So what you see if you put a camera on the far side of a scattering medium, you see basically a speckle pattern that is basically made of many grains, bright or dark grains, which are basically given by random paths interfering through the medium. So the distribution is very well determined. Each spot is diffraction limited. And of course, if you have polarization, it's depolarized. But the key point is it's a complex distribution, but it's coherent. Therefore, just like adaptive optics, you can basically manipulate the speckle for some goals. And there was a very seminal paper about 15 years ago from Velkop and Mosk in the Netherlands, where they show that if you use a spatial light modulator, you can basically control the incident wavefront in such a way that you can basically modify the speckle. And if you put a detector and you optimize the wavefront on the spatial light modulator in order to maximize the intensity, you can get an extremely bright spot through the medium. It's kind of a phase conjugation operation that basically finds a solution that guide light very efficiently to this point. And there is a general framework to discuss that, which is to say that you can discuss the scattering medium as a linear medium, and you have an array of input pixels that you can control. This is your input elements. You have this very complicated system, and through it, you have a CCD camera that is a set of output modes. Okay, and in between, you can define a transmission matrix that will determine how light has been transmitted through the medium linearly. Okay, and what we determined about 12 years ago is a method to measure this transmission matrix by basically sending a basis of modes on the input patterns on the SLM and measuring all the output pattern on the camera, and from that you can determine the transmission matrix. So most setup look exactly like that. You have a laser shining on a wavefront modulator. It goes through a scattering sample that is typically for us just a layer of white paint. And on the far side, you put a camera or a detector. And once you have the matrix, you can exploit the information contained to basically guide light through the medium. For instance, this is what you observe on a camera with flat plane wave illumination. And now, knowing the matrix, you can calculate the pattern to put on the SLM in such a way that you will get a focus through the medium. Okay, and you can also focus to a different point or to a different point or make a multiple pattern and so on and so forth. So in a way, the key insight is if you measure the transmission matrix of a complex medium, you can basically turn it into a lens. And this is really this nice illustration here that shows that we've been perfecting the lens for centuries to improve the quality of the images. But now, and it's just a 2x2 matrix with one parameter that is the focal length in the paraxial approximation. But if you now take this piece of sugar and you know this transmission matrix, that it's extremely complex, you can basically turn it into a lens. And not just a lens, but you also have a very high inclination of rays and scattering in all directions. So you can make it into many, many, many things and many, many optical elements. For instance, you can make it a very high NA objective lens down to numerical aperture 1. You can make it into a polarizer by selecting or controlling the output polarization. It has basically spectral diversity. The speckle depend on the wavelength, so you can basically control which element you want to basically focus, and you can basically make it the equivalent of a spectral filter, or you can make it also just a 2x2 beam splitter cube, or even a more complicated circuit. And I will just show a glimpse of one example we did on this. So the key message, the key take-home message is that if you have a complex medium, it's just a very complicated linear element. And if you know its transmission matrix, you can basically emulate any of this element or combination thereof. So what I want to discuss today in my talk is what we've been doing since, which was really to think of this optical system as something that computes, okay? And the general idea is you have a complex medium with input and output modes, and you have the output, you have a machine that is basically computing some operation, the output on the camera or on some detectors is the modulus square, because it's an intensity of the transmission matrix times the input. And the question we ask ourselves is, can we use that to do some level of computation or treatment of some information that comes? Okay, and I just want to really briefly remind you how it connects to machine learning, which is just about, of course, making sense of data. For instance, classifying images by passing them through some level of neural network. But of course, behind what you have is basically linear algebra. So basically, every dot here would be one image, and you want to basically separate the dogs from the cats. And that looks like this is what the neural network does. But the key, there's a few caveats. That it's of course gets very difficult at the boundary to separate cats and dogs. And there is two problems. The first one is it's not a dimension 2 as I represent here. It's basically in huge dimension, typically 1 million for images. And also it's not always a very linearly separable problem, which makes it difficult. So how does the optics come into play there? This is that the transmission matrix is essentially a random matrix. So if this is an experimentally measured transmission matrix with input and output modes, as we measured in our early papers, and you can basically show that guaranteed by the scattering process, the multiple scattering process, you have this matrix is a random matrix. And you can show that, for instance, by looking at the singular value distribution of its singular values. The other point is it's huge. So the number of input and output modes is basically limited by the area divided by lambda square of this scattering medium. So it can be really in the several millions in and output. So it's typically limited by the number of input-output detectors, pixels of your modulators and detectors. And so you can see the propagation of light through a disordered medium as a multiplication of some input by a random matrix. And this random matrix is actually, and this is what we realized a few years ago with some colleagues from signal processing, a very general operation in signal processing. And I want to give two examples of that. The first one is basically for dimensional reduction. So this is my only mathematical slide, but it really tells you that if you have some input data that you want to treat, you can basically multiply by a random matrix and reduce the dimension of this data to a lower dimension and still maintain basically the structure. So you can basically classify on a lower dimension, just like a PCA, for instance. But random matrices are extremely good for that. Another thing you can do with random matrices is basically do what is called the kernel trick, which is to basically go from a lower dimensional space to a larger space by a random matrix, which is like some kind of rotation of your data set. And you can show that doing that, you can make a very complicated problem and a very nonlinear problem. You can make it linear and so much, much easier to solve. And random projection are very useful and efficient for that. And I'm just putting two references to show you that even though it's not a mainstream signal processing, it's well-known signal processing, as you can see from the number of citations. Okay, for all of this, the beauty is, and that's very useful from the physics point, is you don't need to know the matrix. You just need to know that it's random. That's all you need to perform this operation. So this is why doing it in an analog way is interesting. Okay, and I want to show in the little time I have two examples of the use of this concept on the one hand, to improve optics and in particular imaging from this concept of this computing concept to extract in-depth information from a complex medium. And the other aspect that I just want to briefly mention is how we can improve computing with optics and do some kind of optical machine learning. Okay, so first, from the imaging point of view, how can we extract in-depth information from a complex medium? And I want to show an example in fluorescence imaging, which is, of course, very widespread in biomedical imaging. This is just an illustration from the so-called the rainbow. But what I want to focus on is basically functional imaging, which is that you can, the optogenetic revolution allows you to basically monitor the activity of neurons by modifying them so that they emit fluorescence whenever they are active. So this is, for instance, a zebrafish, the full activity of a zebrafish that you can observe under a microscope. And of course, it works because the zebrafish is transparent. Okay, so when you want to do wide field functional imaging, you basically want to look at the fluorescence from a set of neurons in a brain, and to monitor the temporal activity from this activity. And it works relatively well at shallow depths, or you can go deeper with, for instance, 2-photon excitation and microscopy. But at shallow depths, it works because you have some ballistic light. Light is not fully scattered. So you can observe the neurons that are close to the surface with different ways, also light field imaging and so on. But the problem is, how does it work when you go deeper? So when you go, for instance, a millimeter inside a tissue, light is almost utterly scattered, and it's very complicated to basically recover whatever fluorescence would come from this neuron that are very deep. Okay, and this is, for instance, one example of what we would measure if you have basically neurons that are excited at depth. So what you see is not basically localized neurons fluorescing, but you see basically some speckle, some low coherent speckle from extended and broadband source that are basically blinking. Okay, and the hope is, can we still recover some information on the source? And in particular, we will focus on retrieving this temporal activity. So the dream would be to get the signal from these neurons and in some way recover the temporal activity of these neurons. So going back to modeling what happens, you basically have sources that are basically emitting some light through the scattering medium. You collect them on a camera. And the general insight from this signal processing concept is that the information is not basically destroyed, it's just mixed, but it still remains separable. So you can still recover from this low coherence contrast fluorescence some information about the activity. So you can basically say that if you record this video, you can basically model it as some kind of sum of blinking sources with some temporal activity, time a transmission matrix that you don't know. Okay, so you don't want to do any shaping, you don't want to know the matrix, you just want to basically decode the activity from deep inside the brain. And so we did some kind of proof of principle experiment with DMD that is basically a modulator that allows us to excite some neurons that are just for us some large fluorescent bits, the size of a neuron, about 10 micron in size, which is about quite spatially extended. And the light from these neurons that is temporally coded with a DMD will basically go through the skull, which basically looks like that. So it's very opaque. And you would recover just on a camera the fluorescence pattern that is blinking. And the idea is, okay, what can you do with that? And with what I will show you is how you can decode and recover multiple neurons activity. So the general algorithm we use is so-called non-negative matrix factorization. And it's to take this data set that is this video and say that it's basically, you can factorize into two very thin positive matrix, one being the temporal activity of each neuron, and one being the speckle issued from each neuron. And it's a very, very effective algorithm that even allows you to determine the number of neurons. And just to show you the result from the video I was showing you before, you can recover, this is the ground truth, that is what we're excited with, and we can recover quite accurately the temporal activity. So, and also with a very good correlation of the footprint. So this was of course a nice first proof of principle, but there is a lot of next steps, of course, to go in vivo, look at real neurons, and this is something we're working on, and also on the localization. So now I just have a few minutes to show you some hint about the computing with optics. And what we did was this first experiment a few years back, where we basically display on a modulator some images, which are in this case just handwritten digits, the famous NIST database. And each of these digits will basically go through the medium, is projected on the medium, and on the far side give a speckle that is slightly different. And the key idea is to be able to classify the digits automatically. And the general idea is that this basically behaves as a one-layer randomly connected network. And you can show that you can basically classify directly on the speckle instead of on the original data set. And you get about 2% error on the classification, which is as good as with the original data. In a way, it becomes linearly separable. This is the general idea. Of course, there's no big acceleration there, but it's still, this was the first proof of principle that we could really classify by exploiting the random medium. And why is it interesting? It's interesting because, as I was telling you, it's very large size. So the matrix is of the size 10 to the 6 at 10 to the 6. That's the input and output number of pixels. So if you would like to do it on a computer, it would require terabytes of memory. And you are doing it typically at the speed of your camera and modulators, which is typically kilohertz. So it's a free space analog optical vector matrix multiplier. And this corresponds to about 10 to the 15 operation per second, which is a peta ops, or what you would need a petascale computer to do the same. So it's really, and you do it at a very low energy efficiency. So I just want to mention that we have a spin-off that is really doing and actually commercializing already this device, which is the first optical coprocessor, and it can do many, many things, exploiting this random projection. So inference, training, some linear algebra, there's a lot of use case. I just wanted to mention two other work that I won't have time to discuss today. We also show with the same system that we could simulate a spin glass system and basically accelerate the energy calculation for ground state calculation. And we could also do some kind of linear circuit for quantum information using as a complex medium, not a scattering medium like a layer of white plane, but a multi-mode fibers. And if you're interested, you can also check this paper. So with that, I just want to come to my conclusion. I tried to convince you that imaging in complex media is possible with wavefront shaping and also without wavefront shaping. And of course, it's still very much proof of principle, but it's really one way to get optical resolution extremely deep in a scattering medium. And in terms of optical computing, to convince you that this complex medium provides all-to-all connectivity at large scale and extremely low power consumption. And I just show you some simple proof of principle. And again, I mean, the goal there would be to go to more large-scale problem, new function, and other aspects of optical machine learning. with that, I want to stop, and thanks again all my coworkers and collaborators, and you for your attention. Thank you very much.